Welcome back to Online Calculus 2. This is going to be part 2 of our online lecture on infinite series. In this video, we're going to cover most of our examples related to geometric series and their convergence or divergence. All right, we left off in our last video kind of with the different possibilities for the convergence or divergence of what we're calling an infinite geometric series. This is one where the general term is an nth power or an n minus 1th power. There's two different versions. There's the version for the geometric series that starts with n equals 0 for the starting index. That's where your general term is a times r to the n. And there's the version where the index starts with 1. The general term is then a times r to the n minus 1. These are two different ways to describe the same set of terms in the infinite series. Just depends on the given formula, as you'll see in some problems. All right, what's of primary interest for us is if we can write our general term basically as an nth power. It's very easy to determine the convergence. If the power of r, in other words, r is less than 1 in absolute value, it's convergent. And there's a sum with a simple formula. The sum is a over 1 minus r. And one of the main tips that we're going to implement in the following examples to assist us in this way of rewriting infinite series, their general terms as an nth power, is just to recall a basic exponent rule, which is when you multiply bases, you can add their exponents. What we're going to be doing is kind of the opposite or reverse procedure. This is the kind of starting with the right-hand side of that exponent rule. If we have a sum in the exponent, here m plus n, we can split that to now two separate exponents of base a, where they're being multiplied. All right, let's take a look at our first example, the infinite series coming from Zeno's paradox. This one is a geometric series. We're going to use the version where n equals 0. Recall in our previous online lecture, we described two different ways to write the same infinite series coming from Zeno's paradox. In this case, with n equals 0, our general form form for the term is 1/2 to the nth power, a times r to the n. All right, our r value here is 1/2. That is our ratio by which each term kind of grows by. So we're multiplying by an additional factor of 1/2. And our starting value, the first term of that infinite series is 1. So our a value is 1. Since r is 1/2, in absolute value, that's less than 1, which means this infinite series is convergent. There's a sum. Remember, we said intuitively we expected all the different parts of walking to the halfway point in Zeno's paradox should add up to 2. And notice we get a consistent result here. If we apply our sum formula, a divided by 1 minus r, plug in a as 1, r as 1/2, that expression will evaluate to 2. So we get the correct sum here. We get a consistent result with what we would have liked to have had happen. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, so on and so on forever, does add up to 2. All right, this example required no rewriting of the general term. Let's take a look at a simple follow-up example. Let's say the general term here was 2/3 raised to now the n plus 2 power. Notice the starting index for this infinite series is 0. And what that means for this problem is we want to rewrite it in our first description of a geometric series where n equals 0 and the general term is just an nth power of some number r. So we're going to think here, since the starting index is 0, we're going to try to rewrite this expression to contain an nth power. we can implement that exponent tip, kind of above that we reviewed earlier in this video. We can take 2/3 to the n plus 2 power. Since we're adding in that exponent, n plus 2, we can split that up as 2/3 to the nth power times 2/3 to the second power. Make sure you're comfortable doing that manipulation. You're probably more comfortable going from the right side to the left. When you multiply bases, you would add the exponents. Now we're kind of reversing that. Notice we can rewrite 2/3 to the second power, square both numerator and denominator to get 4/9. And what we get is what we would like, a number a times an nth power. We have a as 4/9. The nth power is an nth power of 2/3. So our r value is 2/3. The value for r is again less than 1, which means this infinite series is convergent. Since it's convergent, we can describe the sum for that infinite series. We have a as 4/9, r as 2/3, and if you plug all those values in, be careful with some basics of fractions for that evaluation of the sum. You're going to end up having in the denominator 1/3. When you divide by a fraction, you can multiply by the reciprocal. So you should end up with 4/9 times 3/1. That should evaluate to 4/3. All right, let's move on to some like actual examples. So let's say example 1 here. This one is a little more challenging. So you're given an infinite series and asked to determine if it's convergent or divergent. If it is convergent, find its sum. This one you can apply exponent tricks to. I'll give you a hint. Take a look at the starting index. It's n equals 1. Your two versions for the geometric series, with n equals 0, we had an nth power. With n equals 1 for the starting index, we had an n minus 1th power. So pause the video, give this an attempt, see if you can rewrite the term here to contain something to the n minus 1th power. We'll check back in a few minutes. Welcome back. All right, as mentioned, the starting index here is 1. To fit this into one of our two standard forms, we're going to try to rewrite this as a times r to the n minus 1th power. Now, if you take a look at the term that you're given, there is already an n minus 1th power in the denominator with 4 raised to the n minus 1. Now we're going to try to have to split that numerator up, the negative 3 to the n plus 1. Let's split that up to contain n minus 1. We'll think n plus 1 is the same as n minus 1 plus 2. Notice if you were to work backwards from the right side, multiply those bases, you can add those exponents. N minus 1 plus 2 would add to the exponent on the left side there, n plus 1. Now notice in the numerator and denominator, we have negative 3 and 4, both raised to the n minus 1th power. And what we can apply is another basic exponent rule, whereas we have the kind of numbers in the numerator and denominator raised to a power, we can rewrite that all as a single fraction to the nth power. Again, you're more comfortable probably going from that right side, a over b to the nth power, and rewriting it as that left side. Here we're kind of using it backwards. We can combine the negative 3 and 4 all as that fraction, negative 3/4 to the n minus 1 power. We're left over with negative 3 squared. And if we rewrite that whole thing, we get this comes out as our general term to 9 times negative 3/4 to the n minus 1 power. We now have our value for a, which is 9, and our value for r, which is the base of that n minus 1th power. R here is -3/4. Again, in absolute value, r is less than 1, which implies our infinite series is convergent. And again, since it's convergent, we have our sum formula, a over 1 minus r, and you should find that your sum here simplifies to 36 over 7. All right, example 2 here is a little trickier. Notice you're not given a general formula for the nth term, or you're not given the infinite series in summation notation. You're just given all the terms written out. Now for this one, try to see if you can find a formula for the nth term and take your pick. See if you can do this as the nth power version or n minus 1th power version for a geometric series. Remember our tip for determining if an infinite series is geometric. Take a look at the ratio of a term divided by the previous term. If you get the same ratio for all pairs of terms, then it should be geometric. Pause the video and give this a try. Let's go through example 2. We're going to try to see if this is geometric by applying our test for the terms. We're going to take a term and divide it by the previous term. All right, so if we go with the second term, -3/2, and divide that by 3, simplify that, work out the basic arithmetic with fractions, you should find that you get -1/2. We're going to move on to the third term, 3/4, divided by the previous term, -3/2. And again, work out that basic arithmetic with fractions. You'll find it comes out and simplifies to -1/2. Let's just do one more pair just to confirm. If we take a look at now the term -3/8 and divide it by the previous term, 3/4, we again get the ratio here simplifying to -1/2. All right, now this is good, a good idea for us to conclude this pattern will continue. And what this is pointing out is that our R value is -1/2, our ratio. Notice the infinite series, the first term is 3, so that's our value for A for this infinite series. So we basically have all of our information. Remember, a geometric series, we can determine its convergence or divergence based off the value of the ratio R. Again, R is less than 1. This infinite series is convergent, and you should find plugging in A as 3, R as -1/2, that you get the sum comes out to 2. Just be careful with that denominator. Notice the formula has 1 minus R in it, but R is itself negative. In that denominator, you end up subtracting a negative, which cancels to addition. So just be careful of that. You should find your denominator of that sum formula becomes 1 plus 1/2, which is 3/2. All right, let's take a look at kind of one final example. So far, we've encountered all of our previous examples in this video dealing with geometric series. We're going to take a look at one last final one here, which is dealing with the question, well, what if the infinite series isn't geometric? What if the term is not an nth power or n minus 1th power of a number? Like what we have here, notice our term is a fraction 1 over n times n plus 1. All right, if you write out a few terms there, in your denominator, you get, for the first term, when n is 1, you get your denominator as 2. The next denominator would be 6. The next denominator, 12. The next denominator, 20. And that pattern continues. We're going to determine if this one is convergent or divergent, but we need kind of an alternate approach since this is not geometric. Notice your terms are not powers of a number. So what do we do? Well, one good starting place is to try to resort to looking at the sequence of partial sums. Now there's a nice little trick here. If you switch out the n's in your denominator for x's, this fraction looks like an expression for which we would have applied the process of partial fraction decomposition earlier in the course. So we can do a similar decomposition here and split that expression, 1 divided by n times n plus 1, into 1 over n minus 1 over n plus 1. Now, if you were to do the partial fraction decomposition, which I encourage you to pause the video, give that a try just to kind of review some of those basic skills from earlier in the course, you get two separate partial fractions. This is the case of distinct linear factors. Here, your factors are n and n plus 1. Your partial fractions would be a over n plus b over n plus 1. And if you work out the algebra, again, pause the video, you should find a comes out to 1 and b as negative 1, which is what we have on our decomposition over to the left there. Now, what does this actually do for us? Let's use this to rewrite the general term and take a look at the sequence of partial sums. Now, our general term here is now this difference of two fractions. So if I start with now n as 1, a sub 1, your first term, is just 1 minus a half. We now move on to our second partial sum. A sub 1 is 1 minus a half. A sub 2 would be 1/2 minus a third. Now, what's the point of doing our decomposition? Notice a nice little cancellation here. In the first set of parentheses from A1, you have negative a half. The second set of parentheses coming from A2, you have positive a half. Those cancel out, giving you as your second partial sum, 1 minus a third. You might be able to suspect what happens with the third partial sum. You have 1 minus a half, and then a half minus a third, and then a third minus a quarter for A1, A2, and A3, the first, second, and third terms of your infinite series. Here, notice we now have most of the terms canceling. The 1/2s cancel, the 1/3s cancel. We're left with 1 minus 1/4. Now, if we continue that process, we actually get a very nice formula for the nth partial sum. All the intermediate fractions cancel. You're left with the starting number, 1, and then the final number, 1 over n plus 1. Everything else would subtract out, similar to the first, second, and third partial sums here. We get as our formula for the nth partial sum, 1 minus 1 over n plus 1. This is an example of what's called a telescoping series. I guess think of what happens with a telescope as you kind of collapse it back together. It kind of all goes to a very small piece. This is thinking of like an old school telescope as like maybe like a pirate would have. And with this expression for S sub n, we can now take a look at the limit of that. Remember our kind of basic definition of convergence of an infinite series is seeing if the sequence of partial sums has a limit. Here, if we take our formula for S sub n, 1 minus 1 over n plus 1, and if we take a limit of that as n goes to infinity, 1 over n plus 1, that denominator gets bigger, so that fraction will get smaller towards 0. And what we find for our limit of the nth partial sum is that approaches 1. Since the limit exists for the partial sums, we say the infinite series is convergent. And the limit that we get there, 1, that actually is the sum that we can assign to this infinite series. All right, that concludes all of our examples for basically this first introduction to infinite series. We're going to see in the following online lectures kind of some shortcuts for other non-geometric infinite series for determining their convergence or divergence.